should be able to defend it. Otherwise, it's better to just leave it as flat priors, right? Okay, any other questions? All right, so these are all the tree building methods that we have discussed. Hey Kunal, this thing is flashing, so maybe the battery is going to die soon.
Probably. We have another battery.
It's here somewhere?
Yeah.
Okay, fine.
Let me go on for a while.
Okay, cool, thanks.
Yeah.
So let's just quickly go over it again. These are the different tree building methods. Least square and minimum evolution, as I said, is not really being used much. UPGMA, neighbor joining, the two clustering algorithms. Neighbor joining is still used to a great extent, but as I said, UPGMA don't use this method. UPGMA falls in the phonetic method of systematics or phonetic school, and parsimony would be cladistic school, right? So these three methods are the character state methods, so they are not using genetic distance. Here they're using genetic distance. So that's one way to classify tree building methods, right? The ones that use genetic distance, and the ones that use character state approach. The other way to classify them is methods that use an algorithm and give you a tree, but do not evaluate all possible trees. So that would be UPGMA and neighbor joining. And the ones that use an optimality criteria, and these ones actually try to evaluate as all possible trees, okay? So remember, least square and minimum evolution actually falls in the optimality criteria based tree building methods. Here you're trying to find the tree with the least difference between observed and tree distance. Here you're trying to find a tree with the least sum of branch lengths, right? And then these are other optimality criteria. Here you're trying to pick the tree with least number of changes. Here the criteria is likelihood, and where you're trying to find the tree with the highest likelihood. And in case of Bayesian, you're trying to find the tree with the highest posterior probability, right? So all of these use an optimality criteria, a criteria that you're trying to optimize, either finding the highest value for that criteria or the lowest value. Remember, parsimony is model free. Models of sequence evolution is integral in case of likelihood and Bayesian approach. You can also correct for multiple hits when you're calculating genetic distance by specifying the model. So in a way, we are using models here also, models of sequence evolution. Okay, so the optimality criteria based tree building methods have a problem, which I'll come to in a minute, and these are the various optimality criteria based tree building methods, and this is what it is they are trying to optimize. Bayesian is in blue, and that I'll explain in a minute. So, you know, in case of optimality criteria based tree building method, you first select the criteria you want to use, right? So you say parsimony or likelihood or whatever, right? And then you have to generate all possible trees. Then you have to calculate that whatever criteria you have picked, right? You have to calculate that for all those trees. And then you have to pick the tree with the highest or the lowest value. Okay? And the interesting thing here really is then not the optimality criteria itself, but the rest of the process. Okay? Because as we discussed earlier, as the number of taxa increases, the number of all possible trees goes up astronomically, right? And beyond 25 taxa, you're not even sure if you have got all possible trees in your data set. And then for each of those trees, you have to calculate that criteria that you have selected, right? And then you have to search for the best of the lot. So this process itself becomes more laborious than the optimality criteria. Okay. So the problem is up to 11 taxa, you can actually build all possible trees. Okay, any computer program will do that. It's not too many trees. Is it there here? So it'll be, I don't know, a little more, much more than that, but still one can build all possible trees. Beyond 12 to 25 taxa, the number of possible trees actually goes up a lot, but you can use a method called branch and bound and still find the optimal tree. Okay? So these are the two possible ways you can get the optimal tree. One is the exhaustive search, the other one is the branch and bound search. Okay? And both of these are called exact methods because it will actually find you the optimal tree. Okay? So yesterday in Mega, under the search options, you must have seen branch and bound also. There's something branch and bound bio or something was written there. Okay? Bio NJ, yeah. Anyway, today we'll take a look at those options again. Exhaustive search is basically you build all trees. And you calculate your optimality criteria for all those trees, right? Branch and bound is between 12 to 25 taxa. The idea here is that certain paths you need not take, and I'll explain that in a minute. Okay, so it's the ideal place to be is, 25 taxa or less, because then you can get to your optimal tree. Anything beyond 25 taxa, it becomes a big problem because you are never sure that you've got your optimal tree. Okay. So what is branch and bound? Okay, so let's say there are 5 taxa, 6. So let us see, what is it calculating here? Let's say it's parsimony. Okay, so you want less number of changes. So what it does, it randomly picks, say, 3 taxa, or the first 3 it's picked here, builds a tree, unrooted tree, then adds the 4th taxa to each of those branches, right? So here it has added the 4th taxa D to this branch here. On this lineage, D has been added to A. And on this lineage, D has been added to C, right? So it does that and then calculates the tree length. Here it's finding 221, here it's 213, here it's 280. Okay. Now these are all 4 taxa situation, right? So now it's like, okay, let's just keep these trees in the bank. Let me now go down this, pick this tree, add the 5th taxa to the different branches. Okay, when it does that, something interesting it finds. Look at the tree score. It's all less than this. Here you have only 4 taxa. It should be less than 5 taxa situation, right? So what has happened, this path, it knows it should not take. Right? So similarly, it can actually eliminate certain paths and get to the optimal tree because it need not go down certain paths. Okay? So this is branch and bound method. So that is what this does. And beyond 25 taxa, you have no way of knowing that you have actually got the optimal tree. And that, as you know, is because of this problem that we discussed yesterday. So in the tree space, there are many suboptimal peaks, and you really want to get to the global optima, but you can potentially get stuck in the local optima. So the way many of these tree building methods work is, you start with a random tree, or you start with an NJ tree, or there's another method called, that was branch and bound. NJ, random, or stepwise addition. Okay, so these are three different ways in which you can start with the starting tree. As we discussed yesterday, if you start with a neighbor joining tree, you're probably closer to optima, but if the neighbor joining tree for some reason is not giving you the right answer, then you will definitely go to the suboptimal tree. A peak. Right? So it's all, these are problematic issues with searching the optimal tree. So the stepwise addition is somewhat similar to branch and bound. So it would basically, after adding the fourth taxa, looks at these three trees, says, okay, let's eliminate this, this has the best score, let's take this tree and add the fifth taxa onto various branches. Again, pick the one with the best score, then add the sixth taxa to the different branches. So that would be stepwise addition. Okay. Yeah, it is a parsimony. Yeah. So it's picking the one with the lowest score. Right? So then what it does, so now we when you have more than 25 species, you cannot use the exact methods. You have to use heuristic search methods. Okay? It may not find you the optimal tree, simply because you cannot draw out all those trees and you don't have the time to even draw them. Forget about calculating the optimal value for those trees and then searching for the optimal tree. Right? It will take a lifetime. So you use something called heuristic method, which is sort of a quick and dirty method to find the best tree. It might not be the optimal tree. So please be very careful when you're using these terms. You are getting the best tree given the constraints of time and computational time and the algorithm. It need not be the optimal tree. Okay. So how does heuristic search method work? Okay. So the way heuristic search method works is, you either first thing you generate a random tree or a tree through stepwise addition or a neighbor joining tree, and then you start rearranging the branches to see if you can get a better score. Okay, and the branch rearrangement, again, this varies from program to program, so you'll have to read up on the material given there. Even the starting tree, what method it's using might be different, so you really have to figure that out. Look at the manual for that program. Okay, so the branch swapping to try and find a better tree. Yeah.
Are we giving a criteria like how many trees should be selected? We are not giving the computer which is
How many trees should be selected in the sense?
initially. It's picking a subset.
No. Initially, it starts with this. No, it starts with either it starts with a random tree, okay, or stepwise addition, which I explained how to. So that's also sort of maybe closer to optimal tree, or it starts with a neighbor joining tree. Yeah, sure.
So all these are subsets, right? Like one after the other, they are happening. 221, 221.
Yes, yes,
Okay.
yes, yes. Yeah. But remember, this is actually, yeah, this is one of the search methods. But up to 25 taxa, this will work, and this will give you the exact result. This will give you the optimal tree. But what we are now talking about is more than 25 taxa. Okay, so yeah, so you have your starting tree, then it starts moving the branches around. And how it moves the branches around is determined by these three methods. And again, you need to, decide which one you want to pick. Some of them are computationally intensive. I think TBR, tree bisection and reconnection, I think is most intensive. Nearest neighbor interchange is, you just interchange the nearest neighbor. So that and that, you interchange, right? Whereas tree bisection and reconnection, let's see if I can see a better tree. Okay, forget it, that's fine. Would be something like you cut the tree here and place it over here. Something like that, right? And then you have subtree pruning and regrafting. This is also, parts of the tree is cut. You prune the tree, put it regraft it somewhere else. So these are different ways to perturb your starting tree. Now, the computer tries that, the program tries that for some time, and you can change that setting also. How long should it keep trying? And then it says, based on, I've looked at so many thousands of trees, here is the best among the lot. Okay, and it might be the optimal tree, I don't know. So, the problem, as we said, if it does that, it might go land up here. So when you're starting with a random tree, it is somewhere in this landscape, that random tree, right? And then you start perturbing it, it can land up in the local optima. Whereas stepwise addition and neighbor joining maybe will start somewhere here. Maybe, we don't know. And maybe you'll get to the global optima. But as I said, if those trees actually land up, taking you to, might be under certain conditions, might be more likely to take you to a suboptimal peak. So these are issues that we have to deal with. So one other method that one can use is random addition of sequences, and then stepwise addition. And this you do it 10 different times. Okay? So the idea really is that you hopefully are starting from different, so basically you are running 10 different heuristic search. Each time the starting tree starts from a different part in the landscape. And hopefully one of those searches will take you to the optimal tree. Okay? So, you'll have to give it some thought. All these settings in the program, whichever program you're using. Read up the manual, find out, what is the starting tree it's using, and how is it perturbing the tree, and the program will also tell you how long it will take to, do some of these searches. So what these commands that I've shown here, tree bisection and reconnection is the most computationally intensive. So these are all from one particular program called PAUP, P-A-U-P. But these settings are also there in most other programs. So you might have to actually look into that. Okay, so any questions regarding this? Yeah?
By random addition of sequences, do you mean like if I have 10 sequences, the and initially if I have 150 for 10, so later on I may change the pattern of how to add the sequence.
Yeah.
1, 4, and then
Yeah.
7. So
Yeah.
that will increase more chances of having the best tree.
Of starting from a different place in the landscape. Right? So that's the whole idea. And hopefully one of those searches will take you to the optimal tree. Yeah. So just remember that whatever program you're using, end of the day, you're never sure you're getting the optimal tree beyond 25 taxa. Okay, so it's the best the program could do, given all these constraints. Okay, so so all these methods use these search algorithms. Okay, end of the day, the heuristic search algorithm is a bigger component of the program than the optimality criteria. Because that search algorithm is more important than optimality criteria. So you might do parsimony, you might do likelihood, and you might say, oh, this is better, that is better. But if your search algorithm is not doing a good job of searching the tree space, then what optimality criteria you use, it's pretty much useless, right? So a lot of emphasis is now on the search algorithm. And different programs do it different ways. And there's a lot of emphasis now on how to come up with search algorithms that are really very fast. Okay, so the optimality criteria per se is not that important. Bayesian approach, the program Mr. Bayes uses that MCMC method. That's basically a search algorithm. Okay, and it's using that that R. What is it? What is R? Acceptance ratio R. But it's using likelihood scores, right? So in that sense, it is not very different from maximum likelihood, because in maximum likelihood, again, you might start with 10 different trees. It's almost like 10 chains, right? And you keep perturbing the tree. It's like links in the chain. And you look for a better tree, and then the only difference is that you make it run for maybe, I don't know, 1,000 generations, and out of that you pick the best tree. And now you've done that 10 times, so you have 10 trees, and among those 10 trees, then you pick the best tree. Right? Anyway, so that's how all these methods work. So, when you're using these programs, please pay attention to the search algorithm it's using and the setting for the search algorithm. We get so obsessed with the settings for example, in case of likelihood, what model of sequence evolution, have we used the perfect model, what is the gamma shape parameter, the alpha value, we get so obsessed with all those things, but search algorithm is actually very important. The same with Mr. Bayes. So you have to play with the settings in Mr. Bayes to make sure again that it has sampled enough trees. Okay. Even if you use a different model, say instead of GTR you use HKY, you'll almost always get the same damn tree. But if your settings for the heuristic search is not correct, then for the same model, you can potentially get different trees. Okay? So please pay attention to the search algorithm. Okay. Any questions so far?
Heuristic and MCMC more or less work in the same way?
No, not really. So yeah, for that you'll have to read up more on MCMC. Heuristic is more straightforward, you know. I think MCMC probably it's much faster. It's just another algorithm that is much faster than the traditional heuristic search algorithms that
But
most
basic
programs.
function, like it is also finding the global optima and
Yeah.
that having 14. But
Well, not
ultimately-
hopefully it's getting to the global optima.
That's
Yeah.
what I mean. Intention is to find the global
Yeah,
optimum
yeah.
here. Same with MCMC, but there we are running 4 chains and from them we are.
Yes. 4 chains, 2 runs. You can increase the number of runs. You can increase the number of chains. You can change the setting on, swapping between chains. All kinds of things you can do there. But to me, it is also a search algorithm. I mean, it is a search algorithm. Okay. Huh.
For a given data set,
Huh.
if I use maximum likelihood as well as Bayesian,
Hmm.
and if the trees are not concordant,
Huh.
how would you interpret that? Can you just blame it on just because there are 2 different ways the algorithms are searching the trees?
That could be. Maybe one of them is doing a better job of searching the tree space. That could be one of the reasons. But Raximal versus Mr. Bayes, we have always got the same tree. I've never had been in a situation where we got different trees. The Bootstrap supports have been different. With Bayesian showing much higher, posterior probability. But the topology has always been the same. But I don't know, we are still trying to understand what kind of search algorithm Raximal is using. I still don't understand. There is no material on it, So the only thing would be that, the search algorithm maybe is not as efficient in one of them, Okay, so let's move on. I'll just quickly go over some of this stuff. I need to update this because this is 2019 material. A lot of these things we are not using anymore. Actually, only these other things we still very much use it. Actually, even this to a certain extent has become redundant now. So selecting, first let me start with bootstrapping, okay? The only thing that is sort of redundant is this. Who was telling me that model test, there is no support now for model test, right?
Jan 2021.
Oh, okay. But it's okay, we'll go over it anyway. First let us go over bootstrapping. Okay. So what is bootstrapping? So it's a simple technique to test the relative stability of a group within a phylogenetic tree. Another way of looking at it is how much support there is for a particular node in the data set. Okay. Measure of reliability of a particular node, support for that node. So it's a sampling technique for estimating statistical error in which the underlying sampling distribution is either unknown or difficult to derive, right? Okay, what does all this mumbo jumbo mean? Here's how you can sort of visualize this. So let's say, you sample 4 species, sequence a particular gene, and you have sampled 1 individual per species, right? And you build the tree, you get this tree. Now, if you were to go back to the field again, sample those 4 species again, but a different individual, and you build the tree again. That's your second tree, right? Now, do this, say, 100 times. So then you'll get, what people call the sampling distribution of your whatever statistics you are trying to calculate, right? It could be, say, height of individuals or whatever per species, but here we are interested in bootstrap support, right? So now you say you have 100 trees, and then you find out in how many of those trees species 1 and 2 are together, and how many of those trees species 3 and 4 are together. Maybe some of those trees, the relationships are different. Right? If in 100% of those trees, the 2 species are together, then your bootstrap support is 100%. Right? Obviously, you can't go back into the field and resample. Okay? So instead, what you do is you resample from your existing data set with replacement. And you do that, say, 100 times or 1,000 times. I'll explain what that is. Okay, what does this node support mean? So how much support there is in your data set for that node? To illustrate that example, here's again the tree, and there are 2 phylogenies. Which among these 2 phylogenies is supported by this alignment? Huh? This tree or first tree or the second tree? First tree, yeah. Right? So you can start off by ignoring the invariant sites. So you can ignore that, you can ignore that, that's also invariant, right? Ignore that, that's also invariant, ignore that. So how many? 3 sites are invariant? Yeah? 4 or 3? 4. Okay, 4 sites are invariant, so 5 sites have the information. Out of those 5 sites, 3 sites support this, 2 sites support this. Right? So one way of looking at it is that there's 60% support for these branches. A crude way of looking at it. Right? So that is what we mean by support. So when you just build a tree, so this is the most parsimonious tree. But how much support is there for the different nodes, right? So that's what we are trying to get at through bootstrapping. Okay, how does bootstrapping work? So as I said, we can't go back into the field and sample. You resample from your existing data set with replacement. What do we mean by replacement? Here's your first bootstrap replicate. What it has done, it has randomly picked one of these characters, put it into the first replicate. So it has picked character number 3, right? And then it will put the character back. So it's not like it takes one character and then now you have only 8 characters here, right? So it's going to put it back, and then it goes on to pick another character randomly, and this time it has picked 6 and puts it back and does that 9 times, because there are 9 characters. In the process, some of the characters will get resampled, right? So now it has come up with the first replicate. Similarly, it does that for the second replicate and so on. It does that 100 times. So now you have 100 data sets. And for each of those data sets, you then build a tree. And then you find out in how many of those trees your taxa are together. Okay? So that's basically bootstrapping. So what's going to happen, because there's more support for this phylogeny, because more sites support that phylogeny, by chance alone, that will be sampled more often. Right? And that will be reflected in the bootstrap replicates. Right? Did everyone understand how bootstrapping works and how the replicates are? So this is a very important method that tells us how much support is there for a particular node. But here is the problem with, I think yesterday we were discussing likelihood and I said, oh, bootstrapping is a problem, and someone pointed out, oh, what's the big deal? If you recall, just to get the most likely tree, the amount of computation we had to do, right? It's enormous amount of computation just to get one tree. Now here we have to get 100 trees. Right? So that's why with likelihood, bootstrapping, 1,000 bootstraps, people have done up to 10,000, but if you have a huge data set, beyond a certain point, you can't do a lot of bootstrapping with likelihood. Because remember, if you say 10,000, that means it is building 10,000 trees. And for each of those trees, it has to calculate the likelihood score.
So I didn't understand that resampling. How does that resampling?
You just take, say a basket and, take 9 marbles, you number them 1 to 9. And then you pick one marble, whatever number it is, you note it down, you put it back, again pick, do that 9 times. What numbers do you get? That's what this is. Right? Does that make sense?
So in what order it gets picked?
Random.
Okay.
It's completely random. Actually, it does not matter at all, if you think about it. Except the problem is, and I don't know how programs are dealing with this. If you are using a neutral region, this is just fine. Or if you're using parsimony. But if you're working with likelihood, right, and it's a coding region, when it gets shuffled like this, what happens to the partitions? I have no clue.
So what I'm saying is, if I have a data set of 500 page sets,
Yeah,
and I'm given 100 replicates,
yeah.
so all those 500 sites will be sampled 100 times.
No. For each replicate, it will be sampled 500 times. And then number of replicates depends on you. You can say 100 or you can say 1,000. Right? Here, the number of sites is 9. So you sample, for each replicate, you sample 9 times. If you have 500 characters, then you have to sample 500 times randomly. And each time you have to make sure you put it back. Otherwise, you will just recreate the same data set with different order of the characters. That's about it.
So is it like more the better or?
Depends on the size of the data set. So if you have a large data set, then ideally you should run more replicates. In this small data set, it does not matter. After maybe 100 replicates, you'll keep getting the same bunch of characters being. But if you have a huge data set, then it makes sense to have more number of replicates. But remember, each replicate now is a new alignment, and the likelihood tree has to be built for that alignment. That means heuristic search and all that, right? So it's basically like building 100 alignments, right? 100 trees, independent trees. Yeah, you have a question.
Why does it always sample and replace, not sample and remove? Because we have duplicates.
No, if you sample and remove, you'll get back this.
But we get a different order, we get a new order.
You'll get exactly the same tree. Then it does not serve the purpose. Same exact tree you'll get. So the idea really is that if you actually go to the field and sample, and if you can capture the variation within a species, that is the ideal world scenario. But we can't do that. But when we are resampling with replacement, hopefully we are capturing that variation within a species that can potentially give you a different phylogeny.
So this is like after some bootstrap replicates, it will be like tree will be like constant. No matter how many times you give, the tree looks same, right?
Tree may still change.
No. I think tree for each replicate you might get a different tree. One way of looking at it is maybe you increase the number of bootstrap support after a while. When you increase the bootstrap replicates after a while, you don't see an improvement in the bootstrap support, improvement in this number. If you just do 100, you might get 55. If you do 500, maybe it'll go up to 60, and then it just fluctuates 59, 61, or something like that, right? But I don't know if people have actually tried it. They must have tried it in the past, but the main problem is just computational time. Eventually you decide on how many bootstrap support based on how much time do you have. With likelihood, sometimes it'll take maybe a couple of days to run 1,000 bootstrap. If you don't have enough time, you'll be like, okay, 1,000. 1,000 is actually reasonable. We have, I think, done max 10,000. Kunal is not here. How many you guys run bootstrap in Raxeman?
So 100.
100, that's it, huh? Okay, 100 to up to 500.
Our trees are like 700 sequences, 800 odd sequences.
Yeah. Then it's very, very difficult.
Yeah.
What about you, Aditya? What's the max you have gone? 1,000. Okay. Yeah.
And it's 1,000, but it took almost 5 days.
5 days. Yeah. So that becomes the main constraint, right? I don't know, we simply don't have the logic to completely go over, try different combination, try to figure out which is the optimal number of replicates. Usually it's time constrained, you stop because your one computer is stuck, and it heats up.
Raxeman does have internal, how do I put it? Like,
It has something called rapid bootstrap.
Yeah, so
right?
it has rapid bootstrap as well as deciding number of bootstraps. So you can set it to auto and it actually decides whether these number of sampled subsets are enough or not. So
Oh,
that is
I
an
see.
internal.
Okay.
So command line version has tons of features on it.
Yeah, so again, we should read up on that. How does it decide that this many bootstrap replicates is enough? Yeah.
Question. So when we give, let's say 1,000 bootstrap replicates, so it will compare 1,000 trees and it will give you the most likely tree last. Is it like it works like that?
No. So there are two ways in which programs give you the trees. Okay. So one is it will first say generate a likelihood tree. Okay. Now this is the likelihood tree. Fine. It's saved. Then it will start with the bootstrap replication. It will do 100 replications, and then it will find out in those 100 replications, replicates, what is the support for these nodes. Okay, so that's one way it does. The other way, and in fact, I think Mega sometimes Mega has these options, and the other way is that it does not first search the most likely tree, the tree with the highest maximum likelihood. It immediately starts bootstrapping, right? And because of the stochastic process of sampling, if you just summarize the trees from your bootstrap replicates, you can actually get a different tree. Right? What do I mean by that? This topology is supported only by 3 sites. The other 2 sites support the other topology. Okay? You run 100 bootstrap, and just by chance, the stochastic process, the 2 sites that support the other topology get picked more often. Right? So when it then summarizes the bootstrap trees, it will show the other tree. Maybe much lower bootstrap support, maybe 55% or something like that. Right? So you understood how, I mean, so there are two ways these programs can actually show, spit out the tree. So you again need to find out what the program is doing. We should not be using trees that have been summarized from the bootstrap replicates. You should first generate your tree and then find out what are the supports for these nodes. Okay. Let's see. We'll in Mega there is that option. We'll see if we have time to show that.
Also in Mega also there is option for Bootstrap. I mean, Raxon also we can do Bootstrap. So
Yeah,
what is
yeah.
the difference in between these two? Both they do different?
No, it'll be the same exact logic. Yeah.
And Raxon there are two types. There's thorough Bootstrap and rapid Bootstrap. So
Yeah, I don't know how these
It's just
two.
difference in algorithms, even I don't know.
Yeah.
IQ tree also uses something called ultra fast bootstraps.
Yeah.
I have no clue what they do.
Yeah. Try to get the literature on it. But the idea is this. I mean, as long as you understand how these methods work and what they are doing, individual programs use different tricks to make it faster, right? So that you'll have to look into the literature.
but still we don't rely on a mega tree. Like people ask for Raxon and Bootstrap and say that mega tree should be fine.
Yeah, so I don't know. I mean, people normally go for Braxml or other programs. If you want to do parsimony, people use POP. Mega is usually used for just preliminary analysis. For some reason, it has this bad reputation that it should not be used for high-end analysis. It might be as good as any other program, Yeah.
How many bootstrap is needed to identify that species is identical or separate? How much support is needed?
Yeah, come to that. Okay, so,
Previous slide, there
Yeah.
was 50% majority rule. So,
yeah.
so this is like the final tree that is most, like more than 50% time that is the final tree this is given.
Yeah, so I'm glad you pointed that out.
Only that is showing.
So 50% majority rule would be, if you take this, summarize the replicates. So what this means is it's going to show nodes that have at least 50% support. If the node has, so if it is this node here, let's say this has 65% support, this one has 50%, then it will show it. If it has less than 50%, it will collapse it. Yeah, so that is what that means. Yeah.
Qualifying. Every node that is necessary is qualifying.
No. It's called polytomy. Yeah. No, but this is when you're summarizing all of that. In your tree, you might get this, right? But because the bootstrap support is very low, less than 50, you don't show any bootstrap support. You just say that nodes that have less than 50% support, I'm not showing. Or you can get into the program and figure out what is the actual support. It might be 35, and you can put it there. So it all depends on you. So some programs actually show it, even if it's very low bootstrap support. In fact, Mega will. Maximum also shows that. Okay.
Almost all.
Yeah. So anyway, let's move on. So in the ideal world, you want more than 95% bootstrap support. but that's very difficult to get. Usually, if you get more than 75% support, that's good enough, right? Anything less than 50, maybe add more data and see if your support goes up. Bootstrapping is very important because when you're reporting your result, you're showing your phylogram, you should always give Bootstrap support. Yeah. Yeah, so I already mentioned that. And of course, in bootstrapping is not applicable in Bayesian because in Bayesian you're getting posterior probability. And the advantage with Bayesian is, it's sort of doing bootstrapping as it's searching the tree space, right? So it is basically summarizing the trees in the desired posterior probability distribution, right? And automatically for each node, it's going to give you the posterior probability. So you don't have to keep running it again, as in case of bootstrapping. Okay, any questions regarding bootstrapping? All right, so let us move on. Okay, so likelihood ratio test. Yeah, we might as well. You'll come across something called likelihood ratio test, where you are comparing two likelihood scores to see if it is significantly different or not. This test can be used to compare two tree topologies, right? And look at the likelihood score of the two trees, and you subtract, one from the other, and that gives you the delta. And then you try to figure out if the difference in the likelihood scores, is it significant or not, right? In other words, if you're looking at two tree topologies, are the two topologies significantly different or not? Or for a given tree, you can also compare models, and figure out if, say, HKY plus G, is it significantly better fit to the sequences than just HKY. You'll get a slightly different likelihood score, and you can then find out whether it's a better fit. So the sampling distribution of delta approximates the chi-square distribution. So you can actually use the chi-square, what is it called? Chi-square table. Yeah, to figure out if the difference that you've got is significant or not, right? And the degrees of freedom here would be the difference in the number of free parameters. So if you remember the yesterday's class when we were looking at, we did model selection in Mega. The first column was number of free parameters, right? No, it was it was the parameters, number of parameters. Each model has a certain number of parameters. So to get the degrees of freedom, when you want to look at the chi-square table, it's just the difference in number of parameters between the two models, right? And then you take this value, the difference multiplied by 2, you get your delta, and then you have the number of free parameters, and look at the chi-square table, and that will tell you whether that value is significant or not, right? If it is significant, then you pick the more complex model, right? So this is what a program called model test does, but I'm told that now it is out of fashion. So model selection nowadays is, BIC and AIC. So where you basically rank order the likelihood scores for the various models, but it's the same idea in the sense that you first generate. Remember, you want the model so that you can use it to get your likelihood tree or your Bayesian tree, right? But to calculate the likelihood of a model, you need a tree, right? So what these programs do is they start with the neighbor joining tree, right? So you get some tree, and then you start applying the different models. And so on. And you have the likelihood score. You rank out of the likelihood score and then the number of parameters. Based on that, you calculate the BIC or the AIC score, and you pick the model with the highest AIC or BIC score. So that's how model selection is done nowadays, right?
Model picking up also requires a tree.
Yeah, because...
Under the impression that it picks the model based on the sequence alignment.
But how? If you remember, when we were calculating the likelihood of a tree, we had a topology, right? So if you just have sequences and you have the model, how do you calculate the likelihood? You need a tree, right? And likelihood method works like that. No, you are actually giving it a tree and saying, okay, now calculate the likelihood. Oh, well, this tree, the likelihood score is whatever. Now let's change the tree topology to calculate the likelihood again, right? So you are actually giving it a tree. It is not like the algorithmic approach where you take the genetic distance and build the tree, right? So even here you have to give it a tree. Okay, so, and we have talked about all these models, various models of sequence evolution. So here's sort of a diagram of how these models are related to each other. The simplest model is Jukes-Cantor, right? If you add two substitution class, which are the two substitution class here? Transition and transversion, you get Kimura 2 parameter model. To JC, if you add unequal base frequencies, remember this is 0.25, 0.25. 0.25 and 0.25. If you add unequal base frequencies, you get F81, Felsenstein's 81. To this, if you add transition and transversion, you get HKY, right? So number of parameters keep going up. So, this is just one schematic diagram that shows, the different models, but here we haven't added G and I. So you can imagine the number of possible combinations. So Vivek was telling me now there are 91 models or something like that.
90 plus.
Yeah. But end of the day, it does not make a huge difference. To me, I think beyond HKY, I don't think these models make a big difference. I don't know, because until HKY, some of the assumption, Jukes-Cantor assumption is really wild. You should never use Jukes-Cantor for sure. But by the time you get to HKY, most of the issues have been taken care of, right? And then to that you add gamma. I think that you are pretty much set, right? And then you are also partitioning your data set nowadays. So I find that a lot of these other models probably are redundant, Okay. Okay, I've already talked about this. Oh yeah, so J model test is also out. AKI information criteria, this is how this would work, right? And BIC is also probably very similar to this, I don't know. So AIC is 2K minus 2 times the likelihood score. and k is number of parameters. Yeah, it's as simple as that, right? So Jukes Cantor has only one parameter. So then this will reduce to just 2 minus